Picture this. It's late. Your terminal is glowing in that dim ambient light of your office.
Oh, yeah, the classic late-night debugging atmosphere.
Right, exactly.
Meh.
And you are staring down this incredibly complex system architecture problem. Now, for the past couple of years, your go-to move in this scenario has been pretty straightforward.
You just open up a prompt window.
Yep. You open the window, you articulate your problem to a massive large language model, and you basically just wait for that single monolithic intelligence to spit back an answer. I mean, you're treating the AI like it's that one mythical 10x developer on your
A
team.
full stack wizard who can supposedly, like, write the database schema, design the front end, and deploy the infrastructure all before lunch.
Exactly. But it's an illusion, right?
Oh, totally. It's a comforting illusion, relying on this idea of an omniscient solo developer who never sleeps. But in practice, I mean, you hit the limits of that single model very quickly.
Because any engineer who has managed a real software project knows that relying entirely on one person is just a massive bottleneck.
Yeah, it never scales.
Never. And as we're unpacking tonight, the exact same principle applies to artificial intelligence. So, welcome to the deep dive. Tonight, we are exploring the next evolution of AI for software engineers, which is multi-agent systems.
We're talking about shattering that single prompt window entirely.
Yes, and building an entire engineering team out of distinct AIs. To do this, we're pulling from a stack of recent AI research papers. The underlying API documentation from emerging frameworks like AutoGen and LangGraph, and a really fascinating collection of real-world devlogs from engineers who are actually building these systems right now.
Basically moving from a single point of interaction to orchestrating this dynamic interacting system. And the literature we reviewed breaks down exactly how these multi-agent teams operate under the hood, the architectural patterns used to structure them, the actual frameworks you can deploy tomorrow, and the very messy bugs that emerge when these agents start interacting.
Which is always the fun part. But let's start with the overhead. Because, I mean, any engineer looking at this is immediately going to be doing some mental math on API costs and latency.
Oh, for sure. Spinning up 5 different LLM calls instead of one sounds insanely expensive.
Right. So why not just write a highly intricate, well-structured prompt for a single smarter model? Like, what is the actual tangible mechanism that makes a multi-agent system outperform a single agent?
Well, the research papers point to context window degradation as, like, the primary failure point of a single model.
Okay, degradation how?
So when you use a single agent for a full stack project, you force it to be a generalist. Its context window becomes completely polluted. I mean, it has to hold the attention for the UI design, the back-end logic, and the security protocols all at the exact same time.
And the attention mechanism just gets spread too thin.
Exactly. The attention mechanism in an LLM fundamentally dilutes over a massive token span. But by using specialization, you silo the context. You have an agent whose entire system prompt is strictly dedicated to finding security vulnerabilities, for instance.
I see. So instead of a prompt saying, write this app and make it secure, you have an agent that just writes the app. Its context is focused solely on the feature.
Right.
And then a completely separate API call goes to a security agent, and its context only contains the generated code and a strict list of security protocols.
Precisely. The system prompt acts as a hard boundary, preventing the model's attention from drifting. And the second mechanism driving this shift is parallelism.
Because single agents are inherently sequential.
Yeah, they read the prompt and they generate tokens one by one. If you need 5 different component files, a single model has to write them consecutively. But multi-agent systems can execute simultaneous work across distributed nodes. While one agent is drafting the core logic, another independent API call is out researching the necessary external documentation, and a third is setting up the testing framework.
That's just classic distributed computing.
Yeah.
You are optimizing for wall clock time by throwing parallel API calls at the problem.
I can definitely see the value there. But, okay, the literature also brings up a third mechanism called debate, which involves having 2 LLMs actively argue with each other.
Yes, the debate mechanism.
From an infrastructure perspective, that sounds like a terrible way to burn API credits. I mean, you are duplicating compute for a philosophical argument in the cloud. How does that possibly justify the latency?
I know, it seems highly wasteful at first, until you factor in the operational cost of an LLM hallucinating in a production environment.
Which is disastrous.
Exactly. Single agents suffer from confirmation bias. Because of how autoregressive token generation works, Once a model outputs a flawed token, its probability distribution skews toward justifying that flawed path. Oh, so it just doubles down on the error.
Absolutely doubles down.
So it confidently lies to you about a library that doesn't even exist, and then writes 100 lines of code implementing that fake library.
Right. We've all seen it do that. The debate mechanism acts as an adversarial filter for exactly this problem. By giving an attacker agent a system prompt specifically designed to find logical flaws in the generator agent's code, you force the models to evaluate their own probability distributions from a totally different angle.
Like an automated peer review.
Exactly. The attacker finds the hallucination, feeds it back to the generator, and forces a revision. You aren't just burning tokens, you're spending tokens on mathematical validation. The output after a debate cycle is significantly more robust.
So you are basically paying for certainty. You catch the logic error at the generation stage rather than finding it when the code is actually deployed and things are breaking.
Which is always cheaper in the long run.
Okay, I buy the overhead cost. We want specialized context, we want parallel execution, and we want that adversarial filtering. Let's talk about system design. Because I assume you can't just drop 5 specialized models into a Python script, fire them all off, and expect them to build a cohesive product.
No, absolutely not. The industry actually started exactly where human project management started, which is the hierarchical architecture.
Makes sense.
You deploy a router agent, basically a manager, whose entire role is to intake the user's prompt, create a JSON array of subtasks, and pass those tasks down to worker agents.
So the manager doesn't code.
Right. The manager does not generate code. It handles the routing logic and evaluates the returned outputs.
It's literally the JIRA model.
Yeah.
The manager takes the overarching epic, breaks it into user stories, and assigns them out. But if I'm looking at this as a systems architect, that router agent feels like a massive single point of failure. Like, if the manager misunderstands the initial prompt, it's just going to delegate garbage tasks. The worker agents might execute those bad tasks perfectly, but you still end up with the wrong feature entirely.
That is exactly the bottleneck developers hit in the early devlogs. The manager agent's context window would just fill up with the sheer volume of subtasks and responses, totally degrading its ability to route effectively.
So how did they get around it?
Well, to solve that bottleneck, the architecture naturally shifted toward peer-to-peer systems.
Decentralizing the flow completely.
Yes. In a peer-to-peer setup, you remove the strict hierarchy. Agents subscribe to a shared context pool, functioning almost like an async event bus.
Oh, interesting.
Yeah, an agent might finish a database schema, broadcast that state change to the pool, and then the front-end API agent just picks it up and begins its work independently.
I really like the event-driven approach. It maps perfectly to how microservices communicate. But managing state in a P2P network of non-deterministic models sounds incredibly chaotic.
Yeah.
I mean, how do you prevent them from talking over each other or getting stuck waiting for a dependency that another agent hasn't even broadcasted yet?
You are hitting on the exact reason the peer-to-peer architecture often just devolves into noise. Without a manager, race conditions become a serious issue. And that chaos is actually why debate evolved from just a mechanism into a full-blown structural architecture.
Wait, really?
Yeah, developers realized they needed to put guardrails on the P2P chaos. So you structure the flow entirely around the adversarial review process.
A pipeline built entirely out of arguments.
Precisely. You define a strict sequence generator, critic, judge. The flow of information is governed by the adversarial process itself. The generator proposes the code, the critic attacks it, the generator revises, and the judge node evaluates if the exit conditions are met.
So it acts as a structural filter for all that noise.
Exactly. It forces order.
Okay, so we have the blueprints, we have the hierarchical bottleneck, the peer-to-peer chaos, and the debate filter. Let's look at the actual stack. If a listener wants to spin up one of these architectures tomorrow, the API documentation we reviewed highlights 3 dominant frameworks, right? CrewAI, AutoGen, and LangGraph.
Right, and they each take a fundamentally different approach to orchestrating these models. Let's look at CrewAI first.
Okay, let's do it.
CrewAI abstracts a lot of the underlying complexity by leaning heavily into role-playing metaphors. Under the hood, it's managing the token windows and prompt chaining for you, but the developer experience involves defining a crew, assigning agents with specific backstories, and handing them a list of tasks.
It's basically a Python wrapper that maps human project management directly onto LLMs.
Pretty much.
It feels designed for a developer who naturally thinks in terms of sequential handoffs and distinct responsibilities. You just configure the team and let the wrapper handle the API orchestration.
Yeah, it's very accessible. But it hides a lot of the execution logic from the developer. If you want lower-level control over how the models communicate, the AutoGen documentation looks a lot more like a network protocol.
So,
AutoGen fundamentally treats the environment like a group chat, leveraging asynchronous message queues.
oh, like deploying a dedicated Slack channel for your APIs.
Yes, exactly like that. In AutoGen, you define the agents and then initiate a chat session. The agents drop messages into a shared log, and other agents react based on specific trigger conditions you define. So the state of the system is essentially just the chat history.
But if the state is just a running chat log and an agent is just reacting to messages, how do you enforce any kind of sequence? I mean, it sounds highly flexible, which is great for a peer-to-peer setup, but it also sounds like you can't guarantee the execution path at all.
Well, you can't always guarantee it, and that is the trade-off. AutoGen gives you incredible flexibility for open-ended problem solving, but if you need rigid, predictable execution, it can be really frustrating.
Yeah, I can imagine.
And that brings us to the third framework, LangGraph, which totally abandons the human metaphors entirely.
LangGraph caught my eye immediately because it frames the multi-agent workflow as a directed acyclic graph, a DAG. It treats the whole system as a state machine.
It is a completely different philosophy. In LangGraph, you define nodes, which are your LLM calls or specific Python functions, and you define edges, which are the conditional logic paths connecting them.
But how do you pass state between LLMs and a graph? I mean, an LLM API call is inherently stateless. You send an array of tokens, you get an array of tokens back. The model doesn't remember what happened one node ago unless you explicitly tell it.
Right, so LangGraph maintains a central state object, usually a dictionary or a strongly typed pedantic model outside of the LLMs.
Oh, outside, okay.
Yeah. When execution reaches a node, that agent processes the current state object, generates an output, and LangGraph updates the central state. Then, based on strictly defined routing functions, it moves to the next node.
So it is orchestrating non-deterministic language models
Yeah.
using highly deterministic routing.
Ex-
You just write standard Python logic that intercepts the LLM's output, parses it, and decides exactly which node executes next. You actually have full control over the execution graph. Like, if you want to know how data moved from node A to node B, you can trace the exact path.
It gives you the predictability of traditional software engineering while leveraging the reasoning capabilities of the models. You're managing the state transitions explicitly rather than hoping the agents just figure it out in a group chat.
Okay, but let's talk about when this inevitably breaks. Because we are spinning up multiple model instances, managing complex state graphs, and handling async message queues, the devlogs in our research stack are absolutely full of horror stories.
Oh, yeah. Every new paradigm introduces terrifying new bugs.
Always. Resource contention seems to be the most common nightmare.
It happens constantly if you don't carefully manage your tools. Imagine you have a research agent and a coding agent operating in a loosely coupled architecture. Without proper safeguards, both agents might realize they need the documentation for a specific third-party API. They both independently execute web search functions, both scrape the exact same web page, and both feed the same thousands of tokens into their individual context windows.
You've just doubled your latency and your compute cost for absolutely zero gain. They're basically stepping on each other's toes because they don't know what the other's doing.
And that leads directly into the next major issue, which is cascading failures. Think back to LangGraph or the hierarchical architecture. If the state object gets corrupted early in the execution, say, the manager agent generates a slightly malformed JSON schema for the overarching plan.
Then every subsequent node is operating on garbage data.
Right. The worker nodes down the line execute their tasks flawlessly. They write perfect logic based on the schema they received. But because the initial state was flawed, the failure cascades silently through the entire system.
You end up with a perfectly executed catastrophe.
Yes, silent failures are the absolute hardest to catch. And then, of course, you have the infinite loops.
Oh, infinite loops in an AI system sound expensive.
Very. Because these models are autoregressive and designed to respond to conversational prompts, they can get caught in conversational deadlocks.
Like, I think we should use Python. I agree, Python is best. Yes, Python is the right choice. And just burning cloud credits forever because neither model has the instruction to actually terminate the conversation.
Exactly. The devlogs note that you have to build explicit safeguards into your orchestrator. You need hard limits on the number of conversational turns or strict exit conditions evaluated by standard kind, so agents don't just talk in circles until your API budget hits zero.
Resource contention, cascading failures, infinite loops. I mean, these are standard distributed system problems, just wearing an AI mask. But there is one concept in the research papers that I really want to dissect. The literature refers to emergent social behaviors inside these systems.
Yeah, that's a big one.
Now, as an engineer, emergent behavior is usually just a polite academic term for a catastrophic bug you cannot replicate. But the papers present it as both a massive feature and a critical risk. Can you unpack this tension? Like, how is a system self-organizing a good thing, but also a total nightmare for stability?
This is really the bleeding edge of multi-agent research. When you connect complex, instruction-tuned models together, they actually start interacting in ways you did not explicitly program.
Okay.
The self-organization is the feature. Like, an agent might realize a Python script is getting too complex and dynamically decide to prompt another agent to write the unit tests for it without you ever hard-coding that specific handoff. The system just adapts to the complexity of the problem dynamically.
The software is literally writing its own operational procedures on the fly. That sounds incredibly powerful.
It is powerful until it breaks. Because if the system is self-organizing, it's no longer deterministic. When a traditional microservice fails, you pull the stack trace, you step through the code line by line and find the exact logic error or the null pointer. But when a multi-agent system fails due to an emergent behavior, how do you debug it? You can't just trace a variable. You are trying to debug a complex, manufactured social dynamic between non-deterministic models.
So you literally have to parse through hundreds of lines of token logs to figure out the interpersonal dynamics of your code.
Yes. Did the system fail because of a syntax error? Or did it fail because the system prompt for the critic agent was slightly too aggressive, and it effectively bullied the generator agent into abandoning a perfectly functional block of code?
I am not debugging logic anymore. I am doing HR for my infrastructure. Like, I'm trying to figure out if my microservices have developed a toxic workplace culture.
I know it sounds absurd to say out loud, but practically, when you're reading through the conversation logs between two agents trying to find why a deployment failed, that is exactly what it feels like. You're tuning the temperature of the model or softening the language in a system prompt just to make the agents collaborate better.
Wow.
You lose the ability to predict exactly how the system will reach its conclusion, which makes troubleshooting incredibly abstract.
Well, let's step back and look at the whole picture.
Yeah.
Because we have gone from the bottleneck of the monolithic prompt down into the actual mechanics of specialized context windows and adversarial debate.
Yeah.
We've seen how tools like CrewAI, AutoGen, and LangGraph let you build these architectures, whether you want a metaphorical human crew, an async message bus, or a rigid state graph.
Mm-hmm.
And we've stared down the dark side, right? The redundant compute, the cascading bad state, and this wild frontier of debugging the emergent social behaviors of your code. So we figured out how to build a team of AIs.
We have. But we really have to remember, right now, everything we've discussed is happening purely inside a text-based sandbox.
Right.
These agents are passing JSON arrays and Python strings back and forth. They are planning and debating in total isolation.
They're just thinking really hard. They haven't actually touched anything real yet.
Exactly. The text is isolated. The missing piece of the puzzle and what the API documentation points to next is how these models actually escape the text generation loop and interact with the outside world.
And this is the setup for our next deep dive.
It is. Next time, we are exploring function calling. This is the structured mechanism that lets an LLM reach beyond text generation.
Awesome.
We're talking about giving these agents the explicit ability to query your databases, call external APIs, run actual code in a local environment, and trigger real-world actions.
Which changes the threat model entirely. And that leaves me with a final thought for you to mull over as you sit there at your terminal tonight. Think about the system architectures we just discussed. We know that multi-agent systems are already exhibiting powerful, highly unpredictable, emergent social behaviors.
They really are.
They argue, they self-organize, they cascade into silent failures, and they bully each other into suboptimal code, all while safely generating text in an isolated sandbox. So ask yourself this: what happens to the stability of your infrastructure when those exact same unpredictable self-organizing agents are suddenly given function calling permissions with write access to directly execute code and mutate your production databases? Think about it. See you on the next deep dive.